Alright, I believe this is the last tutorial video. Yeah, I don't know, it's been fun. First time doing this ever. I basically took this course last semester, so I don't know. It was very different this year. Well, not that different, but there was a lot of stuff we didn't do that you guys did, and there was also stuff that we did that you guys didn't do. So, I don't know. Just acquiring more knowledge. But anyways, what's the first question? Let me find my pen. Where did I put it? Ah, yes, there we go. Okay. Let w equals this, x equal this. They're both element of R3. Find the dot product of w, x, w, and x, x. Right, so we see the dot product is basically, you can just imagine that we have element 1 here, element 1 over here as well. So what we're going to do is we're going to take each element, we're going to cross multiply, right? So it's going to be x1 times y1 plus x2 times y2 plus so on, so on, so on, plus xn times yn. Basically just cross multiply all the elements that we're dot producting. So when we do that, if we have w dot w, well, since we're cross multiplying, we have the same element, that's just going to result in us taking the square. Right? So we can have, what do we have? 3 squared, negative 1 squared, negative 5 squared. It's very important that you keep the element in brackets when you square it. Some people will do minus bracket 1 and then square it. Well, now you have negative 1 instead of 1, right? You should have gotten 1. So make sure you keep the brackets around it. xw, that's just going to be 3 and 6. Negative 1, negative 2, negative 5, and 3. xx, once again, we have the ww case, so we're going to square everything. The next piece is w over w dot w. Right, so we already have w dot w from the from part A. We also have w up here originally, right? So we can just write out the coefficient. Right, this piece will always go to a scalar, and this will just be our vector. All right. So let's see. X dot w over x dot x x. Okay. So we have both of those pieces up here already. And so we just plug those in. Just basically a plug and play game. Oh wow. So let's see. Take the norm or the length of x. And so I just wrote down the formula basically there. We can imagine we have element 1, element 2, dot dot dot, element all the way up to xn. So for the norm or the length, we're going to square root that. And we're going to take the square of each element inside of it, right? So if you just want to imagine basically what we're doing, we're just basically doing this, right? A squared plus b squared, c squared. Okay, so that's just going to end up with that, right? Because c is going to be the length away from some position here. Right. That's what we want to find. So yeah, square all of the elements. Make sure you keep the brackets once again. Square root the whole thing, add them all together, and then you're going to get your result. So we're going to take that fact. We have x. The norm of x is going to go to x dot x within the squares, the square root. You have a square root of 49, which goes to 7. Next thing is the distance, w and x. So you can use either one here, it doesn't matter, right? Because ultimately what we're finding is the length given two pieces. Since we're taking the absolute value, or the norm, with respect to squares, it doesn't matter if we multiply or, you know, if we subtract one from the other or the other from the other, right? We're going to get the same thing. Basically, if you just want to visualize that, because I know words are hard, right? These things are going to go to the same thing, right? X squared minus 2x w plus w squared, and then w squared minus 2 xw plus x squared, right? See? Same thing. Some people were asking, like, does the order matter? So there you go, it does not. So yeah, take your first vector, take your second vector, subtract them in either order that you want. Then we're going to get this result over here. The final step that we're going to need to do is we're going to want to get rid of the norm. Right, so we're going to take the definition up here again, once again. Square root the whole thing, take all of our elements, square them all, add them all together. We're going to get the square root of 74. I'm talking pretty cooked right now. Anyways. So suppose y is orthogonal to u and v. Show that y is orthogonal to every w in span uv. Right? Basically what we can do is we can just imagine we have some w equal to the span of uv. It's very important that we say the span, because what the span allows us to do is it allows us to take any linear combination of u and v with respect to some scalars. We can go backwards and forwards. Right, so we can say that this is equal to u au plus bv for some scalars ab, element of a field. Right, that's going to cover everything, every possible combination. So therefore, we've satisfied the first piece that we want. The second thing is show that it's orthogonal. Well, if we want to show that something's orthogonal, we want to show that the dot product of that pair is going to be equal to 0. Right? So from above, we have that w is equal to the span of this. Well, I just said that we have any linear combination of any scalars. So we can take that fact, bring it down here, so that we have y dot w is going to imply y dot au plus bv equals 0, right, for some ab elements of a field, such that they are scalars. Which is also going to imply that we're going to have y dot au plus y dot bv from the distribution, right? Which is also going to imply that we have a y dot u by dot v, right? That's just commutativity. We can take the scalars out. Those are both equal to 0. The next step is say that since y is orthogonal to u and v, we have a y dot u plus b y dot v is equal to 0. Well, that's going to imply that we're going to have a0 plus b0 equals 0, 0 equals 0, right? Because we have the definition that if it's orthogonal, their dot products are going to go to 0. So we just like sub that in, right? So since they are orthogonal, blah, 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 well, we see that we factored that out over here. That's just going to go to 0, and that's going to go to 0. That's why we can do that. Yeah, so therefore, since y dot w equals 0, y is orthogonal to every w in span uv, because w can be any linear combination. Right, so that's every piece. Okay. What's this? So we have u1, u2, u3, x. Verify the set is an orthogonal. Express x as a linear combination of u1, u2, u3. So to verify a set is orthogonal, I'm going to use the piece that I said earlier. Right? We want to show that all of the dot products are equal to 0. Specifically, though, we want every pair within the set to be equal to 0. Right? So y 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, however many you have, then 2, 2, 3, 2, 4, 2, 5, 2, 6, so on, so on, so on. So if we do that, we have 1 and 2, well, that's 0. 1 and 3, that's 0. And then we have 2 and 3, that's 0. Therefore, since all vector pairs in u1, u2, u3 have a dot product of 0, the set is orthogonal. The next piece is express x as a linear combination of u1, u2, u3. Okay, so moreover, since our above set forms an orthogonal basis for R3, we can use the orthogonal coefficients theorem to find how to express x as a linear combination of u1, u2, u3. It's very important that x is actually an element of the span to begin with. If it's not, it won't work. I believe we'll get a result of 0, such that the result of 0 will result in it not working. The Grinch-Schmidt process, something like you'll get 0 if it's linearly dependent, so that'll fail as well. Just look out for those things. But yeah, so the coefficients theorem is basically we have like ci, that's just going to be with respect to vector x for some vector ui over ui, and dot product. Right. That's going to give us our coefficients for ci with respect to some x for some basis vectors. Okay, vectors in the set. Right, so we're going to use that piece that I talked about. Right. I remember I copied and pasted. I didn't change them. This should be 2, 2, 2. That should be 3, 3, 3. Damn it, copy pasting. Right, there you go. Copy paste, no. But yeah, so you're gonna run through that calculation. You're gonna get the coefficients. I also copy and pasted the c's. This is atrocious. Oh my. Sounded like the guy from Amazing Digital Circus. Okay, so that's it. Therefore, x is equal to c1 u1 minus c2 u2 plus c3 u3. Okay. So that's it for that. What a disaster. Let me save that. I'm going to send that to Discord again. I did not notice that I forgot to change the copy paste. Compute the orthogonal projection of u onto the vector w through this point and the origin. Right, so this is going to be the projection formula. Right, so we have y hat is equal to the projection. Well, we want u onto something, so we're going to say projection u onto w. We put the onto on the bottom, and we put the u inside the brackets. And this is basically just the formula that you're going to use, right? If we had multiple vectors, say we had like u is equal to ab, u1, u2 is equal to cd, well then we're going to have the projection that's going to be equal to, and let's say we have our basis, let's choose y onto something. Well then we're going to get this, and we're going to add. There you go. And you're going to keep going. If you have more vectors, you're just going to keep doing this thing over and over again. So we can just say that we're going to have ui dot ui dot ui. Yeah, that's what you're going to do for that. So in this case, we only have 2, so, well, we're not going to need to add. We're just going to plug in our vectors into there, and we're going to calculate the result. Right. And if you can distribute the scalar in to simplify, I would do that. That's just much easier to look at. Yeah, this is basically just a plug and play again. Let y equal this and u equal that. Right, y is the sum of 2 orthogonal vectors, one in span u and one orthogonal to u. So once again, this is going to involve the projection. However, we're going to add a little piece to it at the end. Right, so we're going to find y hat equal to the projection uy. That's going to give us our first orthogonal vector in the span of u. So plug and play y onto u. So y dot u over u dot u times u. And we're going to say that this element over here is going to be the element of our span. The next piece we have is we can decompose y into y hat and z, right? The complemental pair. So from this, we have y hat, but now we need z. So we can just simply move it over. Z is equal to y minus y hat. Find our z. And, well, this is the other vector that we wanted, right? Therefore, y is equal to y hat plus z, where y hat is an element of the span of u, and z is orthogonal to u, right? It's a nice piece. True and false, my favorite. That was really bad, actually. But. Right. If x is in both w and the complement of w, then x equals 0. Right, so we see this, it's true. If x is in both w and the complement of w, then x dot x equals 0. Right? And so we can combine that with the fact that from x dot x is equal to, well, the first element squared, the second element squared, up to the nth element squared, where we're adding them all. We conclude that x must equal 0, as a non-zero x would imply that the dot product from x dot x is equal to x first element squared, second element squared. Well, that's going to imply that x dot x is greater than 0. Right? Because the property of our dot product, complex or real, is such that we have by the square dot product property over the reals and conjugate pair property over the complex plane. If it's non-zero, it must be greater than 0. Right? Basically going to use that. For any scalar c, we have the norm of cv is equal to c, the norm of v. This is false, right? We can just suppose that we have c is equal to I, and v is equal to 1, 1, 1. Then we have the norm of cv is equal to the norm of I, v, which is equal to the square root of 3. However, c, the norm of v, is equal to I, the norm of v, which is going to be equal to square root times I, right? Square root 3 does not equal square root 3i. So therefore, the norm of cv does not equal c, the norm of v, for all c. That's just the only thing that we wanted to show. It says for any, so we can just show that it fails for 1. We're done. More specifically, though, we want the norm of cv equals the absolute value of c times the norm of v, right? This would be good. All right, what's c? for an m times n matrix A, vectors in the null space of A are orthogonal to vectors in the row space of A. So we see that that is true. I gave an examples, right? So we have some m times n matrix. So let A equal, well, 3 columns, 2 rows. I like to do with something that resembles the identity matrix, just 'cause it's easier to deal with. Yeah, so we solve for the null space. We see that we only have one free variable. That's going to be in our x3 slot. So therefore, we're going to have 0, 0, 1. The row space is just going to be with respect to the pivots. The rows are our pivots, right? So we're going to have 1, 0, 0, 0, 1, 0. Store them in our columns. We're going to have 1, 0, 0, 0, 1, 0. So that's asking they are orthogonal vectors. The null space of A orthogonal to vectors in the row space. So we have a null space and a row space. So now we're just going to do the null space, dot product of the row space. We want to see if they're equal to 0. If they're all equal to 0, then it's going to be orthogonal. So we have 0, 0, 1, dot 1, 0, 0. Well, all of our zeros are just going to multiply together, right? That's going to give us 0. Is equal to 0, 0, 1, dot 0, 1, 0. That's our second piece. Right? This is V1, V2. Let's just call this V3, V3. Well, so they're all equal to 0, so therefore the entire thing is orthogonal. That's just an example. D. If W is a subspace of Rn, then the complement of W is also a subspace of Rn. So this is true. I gave an example once again. Let W equal the span of 1, 0, 0, 0, 1, 0. I just like this piece. Well, that implies if we store a matrix like this, that we're going to get A equals to, well, first vector, second vector. Then what we can do is we can store them as rows in a matrix, right, to find our complement. So take the transpose, basically. Then what we're going to do is we're going to find the null space of our transpose matrix to find the complement, the span of our complement. That just gives us, once again, similar up here, x1, x2 equals 0, x3 is free, so t, take that out, solve the null space as you usually would, equals to the span, 0, 0, 1, equals to the complement. Right. We can also check, similar up here, that it's orthogonal, and we see that yes, it is. Most important thing, though, is are they both of R3? And yes, we see that it is. Right. Alright, what's the next one? Not every linearly independent set in Rn is an orthogonal set. Yeah, so this is true. So we can suppose, just an example once again, right? Because we only need an example to disprove that every linearly independent set is. Right, so let B equals 1, 0, and 1, 1. Those are of R2. Then B is linearly independent, as if we were to set up a matrix and solve for our scalars. We see that C1 equals C2 equals 0. Those are all of our C's. So that would be linearly independent. However, we notice that the dot product is not equal to 0. It will be equal to 1. Since it's not equal to 0, they're not orthogonal, right? So that means, therefore, not every linearly independent set in Rn is an orthogonal set, right? We've shown that it's linearly independent in Rn, but it doesn't work. Right? And F, an orthogonal set is always a basis for the subspace spanned by the set. We see that's also true. I believe he gave a proof in the notes. It's just going to be a lot to go over. But yes.